All right, let's get started. A couple things just right off the bat. I'll go ahead and mention I'm not really feeling very well today, so if I'm a little out of it, just bear with me. Another thing, and I think this is kind of my fault, I took my microphone with me last week because I had to record a lecture for co-op, and I didn't really charge it very much. I was like, I was in concrete design, an hour ago, and the mic kept dying. So if the mic dies, we might have to scrap the recording. We'll just see what happens. A couple quick announcements. Don't forget you have a homework due on Monday. For those of you that are juniors and are thinking or planning on taking Engineering 452 next semester to go into the senior design sequence, we'll be sending emails out soon, probably within the next few weeks. So just pay attention to your emails. So that, for those of you that had senior design this year, basically what happened is we'll just tell you, are you good, assuming you pass your classes, what classes do you need to be concurrently taking next semester, and the like. So, one other thing I'll mention, after today, you really want to start bringing your manual to class because we're going to start using it on a regular basis in class. So we're actually going to open it and leaf through some things today. I just wanted to make everybody aware of that. It's not totally necessary today, but it is kind of nice. So today we'll talk about the manual and some general properties of steel, and then we'll get into tension members. But before I do, I want to open it up if anybody has any questions about homework 1 that's due on Monday. And so this is our last meeting before that homework, before you all turn that in. So if anybody has any questions, I'd be happy to address them. Anybody have any questions? I did have a question. Which one was it? Which site? Which site was the seismic one, right? But which location? Was it both locations or just one? Caltech? Yeah, there are actually 2 site class Bs. There's rock, and then what's the other one called? I can't remember. Estimate, yeah, go with rock. So I don't really think it affects your spectrum very much for that lookup, but go with rock. Oh, it did? Okay. Yeah, well, no, it would be. Sorry, I'm out of it. So go with rock. Sorry. Any other questions? Okay. Okay. So we spent the last week talking really about this, the concept of loads and resistances in structures, the idea that the resistances have to be greater than or equal to the loads. And we talked about wind and seismic predominantly in here because we talk about gravity loads in concrete design. But the idea is I want you to understand that end of the equation a little bit. From here on out, we're going to be talking about resistances. How strong is a bolted connection? How strong is a welded connection? How strong is a beam? How strong is a column? So that we can size those appropriately to adequately resist those loads. Now, before we do that, we have to discuss a very important reference. That was actually a really cool insert. Did you all see that? They had this when they sent the steel manuals out. There was a little leaflet that says it's an important reference. They had a dog on there. Who got the right? What happened?
I feel gypped.
Yeah.
I didn't get a dog.
Now, I'm gonna tell you something. I'm gonna tell you something right now. Here we go. Yeah, you just gotta pass it around just because it's awesome. Yeah, just make sure that she gets it back. But it's just awesome. I can tell you something right now. If AIS, so I have a little 14-pound Jack Russell Terrier. If AISC decides to sell milk bones but they're shaped like I-beams, I'm buying them. That's just what's happening. That's just what's happening. So that's a hint. That's what I'm suggesting it on the recording. Hashtag. I don't think that AISC watches these. Yeah, I don't think so.
What if they need a little refresher course?
They wrote it. They're good. Let's talk about the steel manual. I actually want to talk about the book. It is one of the most common references for civil engineers, period. Okay? It is published by AISC. AISC is the American Institute of Steel Construction, and they are basically the technical specifying body for steel, period. That's what they do. Now, they obviously they're the American Institute of Steel Construction, but one of the things about steel beams is steel beams really don't care whether or not they're in a building in Detroit or a bridge in Czechoslovakia. Steel behaves the same. So a lot of these provisions, a lot of them get duplicated everywhere. So this is just some very fundamental info, and there's a lot of very good data and resources in that manual, and we'll explore a lot of this throughout the semester. Now, the way that I think of the manual, you know, there's really like 17 or 18 parts now, but really the way I think of the manual is in 3 chunks, okay? The first chunk is the very beginning, and you can start flipping through the first few pages, and you'll see what I mean, because if you start going through like the tables of W shapes and L shapes and C shapes and whatnot, the first part has all of the fundamental design, detail, dimensions, etc. So that's the first part. The second part is actually the part at the very end, because the part at the very end is the actual specification. That's the document that tells us how we design steel structures. So the design equations, the limits, etc. Everything else, what's going on in the middle, is why you bought the manual. You can tell those sections because they look like this. Now, if you start flipping through the manual, you'll see a bunch of tables that have green numbers and blue numbers for shaded and unshaded. Remember, in this course, just because it makes more sense and it's where the industry is trending, we're going to utilize LRFD. So whenever there is a colored table, we use the blue numbers, not the green ones. So let's get that right off the bat. Don't look at the green numbers. Green numbers don't exist. Yeah, see, you're using the 15th edition. What happened was this. There were actually 9 allowable stress editions and 3 LRFDs. So there are 12 manuals. And so what the steel industry said is, let's just publish it in one and call it the 13th edition. So the 13th edition was the first edition that combined ASD and LRFD. And so that was 2 editions ago, so now we're on the 15th. So that's what we're on. But again, make sure that you're using blue numbers. Let's talk about steel. Seems to be a relevant topic with this course. Particularly what I want to talk about are the properties of steel. Okay? And I want to start that discussion with this. Okay? Has everybody seen this before at some point or another? This is a stress strain curve for structural steel. I'm getting there. My goodness. This is what you get when you take a bar of steel and you apply axial tension and you yank on it until it fractures. This is what you get. Now, there are a few key regions. This first region over here on the left is the elastic range, from here to here. So remember what elastic behavior means. You apply load, you let it go, it snaps back to its original condition. More often than not, we like to ensure that structural steel limits, or we try and limit structural steel's behavior to that range. Not always. There are some instances where yielding is going to happen whether you like it or not, so we do need to understand the nonlinear range. So once it yields, you have a region of perfectly plastic behavior, so it continues to deform under no increase in stress, and then you get your nonlinear behavior. Now, if you want some scale to this graph, the best way I can explain it, that I've heard it explained, is let's say that this is a football field. And here's the line to this end zone, and here's the line to this end zone. From here to here, this linear range, that's a 1 yard line. Okay? From here to here, that's a 10-yard line. And so steel has a very remarkable parameter, or remarkable property, and that property is ductility. If you ever hear the term ductility, ductility means a material's ability to withstand inelastic deformation. And steel is amazing at that. It can withstand a lot of inelastic deformation. In World War II, when cities in Europe were getting bombed, it was not that uncommon for houses and folks' homes. They would put sort of like a steel cage inside the house, so that if the bombs were being dropped, they would go inside the cage, so that the cage would absorb the force of the roof collapsing on it, and they would live. That's actually that was a very common instance in World War II, and that's because steel is a very, very ductile material and was able to absorb all that energy through its ductility. So just a random piece of history. If I zoom in on that linear region and that perfectly plastic region a bit, remember, once you pass the elastic range, you get locked in permanent deformations. So if I apply the stress all the way to, say, up here, and I let it go, it doesn't snap back to its original condition. It snaps back to a point where it's got permanent deformations locked in. And so that's past yielding, okay? And so that's something I really want everybody to understand, because some of our limits are going to be based off yielding, and some of them are going to be based off fracture. Everybody good? I'm going to drill these numbers into the back of everybody's head before I'm done with you. Don't forget that the modulus of elasticity of steel is 29,000 KSI. That's the relationship between the applied stress and the resulting strain in the linear elastic range. That value is constant for any grade of structural steel. You can set your watch by it. And then the unit weight of steel, 490 pounds per cubic foot. And that value is critical to computing, loads on systems and whatnot. Any questions? Now, excuse me. E and the unit weight are constant for the grade of steel chosen. It doesn't matter what grade of steel you're looking at. It's always the same E, and it's always the same unit weight. When you look at different grades of steel, you get different yield stresses and tensile stresses. So the yield stress is when it starts experiencing permanent deformation, and the ultimate tensile stress is the largest engineering stress that it experiences before it fractures. Okay? Now, when you purchase a different grade of steel, a higher grade of steel, that's what you're getting. You're getting an increased Fy and an increased Fu. So where do I find these properties? I want everybody who has their manual to turn to page 2-48. I will give you a second. Has everybody got that? Before we start looking at the table, see that little green star on the top right? That is a page in your manual that you ought to put a tab in. You are going to be turning to that section of the manual from here on out. And you will need to be able to reference that table for pretty much every problem that we do in this course, period. So because it is so important, I put a star in the lecture. So whenever you see a star, put you a sticky note there, put you a tab there, you'll be referring to that. Now, if you look here on the left, it says Table 2-4, and it says applicable ASTM spec for various structural shapes. Table 2-5 is for plates. And then if you actually turn the page, it's for bolts, but we won't use that table because we'll use the direct FNV and FMT values later. One of the things that I want to look at with this table is this. So let's take a look at A572 grade 50. We'll say it again. A572 grade 50. What is the FY and what's the FU? 50 and 65. So if I give you a problem with an element that's made out of A572 grade 50, what's the yield stress? What's the tensile stress? It's right there. All right? Now, what about A36? What's the yield stress? 36. What's the tensile stress? It's a range, so it's 58 to 80. Now, if you're the designer, what do you use? Say it again. You said 80. What did you say? You said 58. Who says 80? Who says 58? It's 58. Now, he's right.
Yeah.
Why?
Because that's the most conservative.
That's exactly right. When you are designing this bridge that is going to carry traffic in Huntington, and you know that your grandma is going to be driving over this bridge to get groceries every day, and you think, oh gosh, I don't want anything to happen to grandma, what are you going to assume? Well, think, if you assume a lower value for the stress, that's going to result in a more conservative, larger design. Now, I'm sure that some of you are thinking, why the hell did you put the range? Just put the 58. Why'd you put the range? If you just keep it simple for us. There is a little bit of a convoluted reason why the range is there. I'll try and keep it as short as possible. The real reason is seismic. So back in 1994, there was an event called the Northridge earthquake. And what happened was, and this was in 94, back in 70s, 80s, up till the early 90s, the steel industry was telling everybody who was designing in seismic regions to use moment frames. Now, what happens with steel production is this. Those values that you see in that table, they are expected minimums. So put yourself in the shoes of a Nucor Yamato steel. The last thing that you want to have happen is you don't want to be sued for when some building collapses because you said that the yield stress for your material was 50 KSI and it turns out it was 30. So what you do is you say, well, I can promise 50 because what I'm really producing is 55, 60. So usually those values are minimums anyways. What happened in Northridge was some of the moment frames that the steel industry thought were fine and were going to perform beautifully under earthquakes, they were experiencing a lot of cracking. Now, it wasn't the end of the world because ultimately the structures that we're talking about, there were no fatalities. That wasn't the issue. But the issue was we thought it was going to be fine, and they weren't. So what happened? Well, in short, the larger your FU, the lower your ductility. So we were assuming all this ductility, we really didn't get it. So when they report those ranges, it's really for you as the engineer to know if you're using this in an application where you need ductility, pay attention because you might not get as much ductility as you think. So that's why they report the range. So I know for regular everyday structural design, you'd think just give me the minimum, but that's why. I know it's a long convoluted. What?
So apparently they all thought getting a max.
Well, they're telling you the range because they want you to know that with that larger FU value, you're getting a lower ductility. So, okay. Everybody good? Okay. Let's talk about some terminology, just so everybody's aware of this. So if you see me refer to, or if you hear me refer to, say, a channel, what I'm talking about is a steel element that has a C-shaped cross-section. If you hear me say an angle, I'm talking about an element that has an L-shaped cross-section. Now, we actually don't use I-beams anymore, okay? And that seems a little weird. Well, when you first hear it, because you say, well, Dr. Mike, that sure looks like an eye to me, The reason why is because the American Standard I shape that we produced back in the day had a very significant, or had a very specified cross-section geometry. It had certain slopes on the flanges and whatnot. And with modern rolling techniques, we really don't produce that cross-section anymore. The most common I shape, if you will, that we use is what's called a W shape. And a W shape is called that because the flanges are wider than a typical I-beam. So if you hear the term wide flange or a W shape, it's an I-beam, but it's an I-beam that's produced with more modern techniques. So we will be using wide flanges this entire semester. So just something to be aware of. The S shape does have smaller flanges, and we'll reference S shapes here and there, but not very often. Wide flanges just use the steel more efficiently. No. No. That's a good question. So you're talking about an H-pile. Is that what you're talking about? Well, let me say one thing about that because, well, I'm going to give you an example where it would make sense to refer to it in that fashion. So for those of you that have had foundations, have you heard of an H-pile before? Okay, all right. So if you go to table 1.1, you'll see the W shapes and whatnot. But I think it's table 1.4, you'll see HP shapes. And HP shapes are the piles. In bridges, when we're using piles, let's say for abutments, for the foundation at the end of an abutment, we actually place those in weak axis bending. So instead of facing it like an I, we face it like an H. And there's a reason for that. Because under thermal conditions and movement of the ground and whatnot, we'd like the abutment to be a little bit more flexible. So we actually place it in that H configuration. But if you're talking about like a building, I mean, nowadays they're just using W shapes. Now, if they want to call them I shapes or H shapes because they're looking at it this way or this way, I'd tell them just move here. No, I just want to make sure that the terminology is sort of consistent with today's practice. If you hear the term H-piles, they're talking about foundations. And there are a particular series of shapes produced by the steel industry for piling. So it's just a steel shape, a steel cross-section. It's a little thinner, and the yield stress is a little lower because you don't really need it because you're relying on friction and tip capacity and whatnot. So. But yeah, it's just a different shape. Any questions? All right. Let's make sure we're all clear on terminology. Okay? When you have an I-beam, this is the flange. This is the web. So, for instance, if you have an angle, this is the leg. So don't ask me, like, what's this called? It's a leg, too. This is a flange, too. I've been asked that before. So, but if you hear me refer to this stuff, I just want to make sure that everybody's on the same page in terms of terminology. Okay, sound good? All right. Let's go to part 1. Because I want to look at this. I want everybody who's got your manual to go to part 1, and I want you to find a typical W-shaped table. Okay. First off, I think you should put some tabs in part 1. But I don't want to tell you here's exactly which sections you need to tab because I think that this is sort of up to you. At the very least, I would place a tab at the W shapes because we're going to use W shapes all the time. In my manual, I have a tab at the W's, at the C's, at the angles, and the WTs. That's where I have my tabs, because those 4 cross sections are by and large the most commonly used in this course. W's, C's, L's, and LT's. But if you want, you could get nuts with it and put tabs all over the place. At a bare minimum, put a tab on the W sections. At a bare minimum. You will be looking at these tables every day. Every day. So the yield stresses and these tables, that's sort of what I think is part 1 of the manual. All the fundamental dimensions and parameters that we use in steel design. Okay, sound good? Now, a couple things. First off, actually pay attention to these, okay? And I'm serious, because I'll have students go, well, what's the flange width? I need the flange width, but I don't know what the letter is. It's B sub F. It's B sub F because that's what it says right there, okay? So for instance, if you need to know the thickness of the web is what? T sub W. Sound good? Now, that brings up another question. If I look at the depth, so the depth in the manual is reported from the very tippy top to the very, very, very bottom. Which value do I use when I'm doing calculations? Do I use the 27.6 or do I use the 27 5/8? We use the 27.6. In this course, we only use the decimal values. Okay? The decimal values are for design computations. The fractional values are for detailing, so for drafting and drawings. Like when you go out to the construction site, you need to know how wide the flange is, you pull out your tape measure. That's what it's going to say. Now they get these values from collecting data from the steel mills every so often. So that's why when you get a new manual, the tables get updated ever so slightly from edition to edition. So this one might have been 26.8. This one might have been 24.8. This one might be 0.459 or whatnot. They get updated ever so slightly from edition to edition. So it's just something to be aware of. Sound good? So again, decimal values. I say that, and I know on homework 2, somebody's going to use a fractional value. And I'm going to go, no. Yep. Now, let's talk about naming. So let's say you have a W27 by 129. What the heck does that mean? Well, the W refers to the shape. So the W means it's a wide flange cross-section. So what does the 27 and the 129 mean? Well, the 27 is about how deep it is. About. It's not exact, it's about. It's because all of those shapes are produced according to arguably a similar rolling schedule. So you'll have a family of shapes that are all listed as W27s, and their actual depths might be 26.5 to 27.8, sort of hovering around the 27 range. So that's what the 27 means. It's about 27 inches deep. What does the 129 mean? It means that's how heavy it is. A W27 by 129 weighs 129 pounds per foot. Okay? So you never need to do any math to determine how heavy a rolled shape is, or a wide flange is, because it's all right there. Okay. So far so good? Yes? Yep. Talking about corrosion and section loss. Sorry, what? You are talking about a very, I won't say hot button, but a very intricate and difficult issue in steel design. Like, how do you measure the thickness of a web that's 12 foot deep? You can't put a caliper on it. You know, you just can't do that. There are some really high fancy scanning techniques where they'll develop a 3D rendering of the girder. I was actually at PennDOT, and they were not too long ago, and they were showing off this scanning system that they had. It was really neat. And what they would do is they would have an I-beam, right? And they would sort of, it was almost kind of like a GIS type equipment, but what it would do is it would sort of collect point cloud data along the girder. And so what you would do is you would take that point cloud data and you would overlay it on top of an ideal I shape. Now, in that instance, what they were trying to do was measure girder imperfections during fabrication. See, nothing on this earth is perfectly straight or perfectly flat. That's why you have tolerances. You could arguably use something similar. There would be error, and you'd still probably be doing it from one side to another. It's difficult. The only other thing I can think of is build a really big caliper. I'm not kidding. I'm really not kidding. Some super big caliper. Yeah. But nobody would use it, except for like 2 firms that spent, $80,000 on it. Okay. Are there any questions? All right. I do have some like movie time for you. Okay. Let's talk about tension members. So in this course, we're going to learn how to design some very, categorized elements in structural steel. So we're going to learn how to design a beam. We're going to learn how to design a column. We're going to learn how to design a bolted connection. Why are we starting with tension members? Tension members actually are, in a building, probably the least common element that you see. So why don't we start with tension members? Well, first off, they're not unused at all. I mean, if you have a truss, some of the elements are in compression, some of them are in tension. So you are going to see tension elements there, and you're going to see them in braces in buildings. But why do we start with tension members? We start with tension members because theoretically and conceptually, they're the easiest to start with. They're not difficult. Sigma equals P over A, solve for A. That's it. But what I'm trying to do with this first topic in tension members is I want to teach you about the process of design, but the other thing, I want to teach you how to use this. I want to teach you how to use the manual. It's daunting. It's huge. I want it to not seem intimidating, and I want you to understand how these documents work. And so I think it makes sense to start with something that's easy to digest. A lot of the theory with columns and beams is you got to sort of take some time and digest it. This stuff's pretty simple, so I think it's a good place to start. Now, the mechanics are fairly straightforward. All right, this is literally day 1 of mechanics of deformable bodies, and I'm telling you, it's easy. You have a bar, you're yanking on it. It has a cross-sectional area A. You're yanking on it with some load P. The axial load P, cross-sectional area A, the stress is P over A. So if we're trying to determine how much load it can hold, solve for P. P is whatever the limiting stress is times the area. Now, does anybody have any questions about that? That's basically it. It really doesn't get much more complicated than that. Now, there is a definition that we need to introduce right now. So I propose that for a tension member, the way the math works and the way the theory works is the maximum load that an element can withstand is whatever the limiting stress is times the area. So what's the limiting stress? How do we define that? So I need to introduce to you a condition or a term called a limit